Hello. In the last section, we have studied about error, combination of errors, and in question 2.7, we have seen the reliable and unreliable digits. Something we have we have ignored the last digit. The error is 0.11, and we considered the error is only 0.1, and that is because the main absolute value was 2.6. So the up to first decimal place it was the unreliable digit, so we ignored the last digit. Now we will study the significant figures using the same concept that is used in question 2.7. We will see more in depth here the rules that are that governs what will be the significant figures, and how we have to means realize, because significant we have to write every answer means we will go through many chapter in class 11th and 12th, and we have to go to solve we will solve many problem that the question will come up to 6 to 7 decimal places. So how we will write, we cannot means up to class 11th or 12th we don't have access to calculator. So the students are always confused up to how much decimal places I will write. So the rules that we study we are going to study in this chapter will be applicable in all the problems you will solve till class 12th. Many values are means if you see a parallel combination, you will get the value here 67.7 plus 1.8, and maybe if you go in more devices are in parallel, you will get the many up to many decimal places answer. So up to how much places you will write, we will going to study as a rule, and let's start. As discussed above, every measurement involves error. Thus, the result of measurement should be reported in a way that indicates the prediction of measurement. Normally, the reported results of measurement is a number that includes all digits in the number that are known reliably plus the first digit that is uncertain. The reliable digit plus the first uncertain digits are known as significant digits or significant figures. Reliable and unreliable in two up 2.6 plus minus 1.11 0.11. We said that this is the first unreliable digit. This one up to first decimal place. So we have ignored this digit, and we have write 2.6 plus 0.1 plus minus 1, because if we add 6 1 into 6 it will become 2.7, and if you subtract that, that will become 0.5. So 2 is not changing here, so 2 is what is 2 is a reliable, and first decimal place this 6 is here, this is the unreliable digit. Very important to understand here, because that will build our concept unreliable and reliable digits. If we say the period of oscillation of a simple pendulum is 1.62 second, the digit 1 and 6 are reliable and uncertain, while the digit 2 is uncertain. First I read wrong, it is certain. Thus the measured value has three significant figures. The length of an object reported after measurement to be 287.5 centimeter has four significant figures. The digits 2, 8, 7 are the certain digits, and the 5 is uncertain. Last digit will be the uncertain. Whatever the error will be involved, the experiment will be such that the error will be only involved in this digit. Not means if the error will impact, that must impact that digit, not this 287. Clearly, reporting the results of measurement that includes more digit than significant digit is superfluous. It and also misleading, since it would give a wrong idea about the precision of measurement. Means if suppose our vernier calipers has 0.01 centimeter precision, and after measuring it we will find that something more than 3 digit we are calculating. 1 centimeter. So this one is very insignificant, because even the measuring instrument cannot able to read it. The measuring instrument that we are using in that experiment, not in means spirometer, of course it will able to read that, but the one the equipment using which we are measuring that, does not have that precision, or I will call it resolution. The rules for determining the number of significant figures can be understood from the following example. Significant figure indicates, as already mentioned, the precision of measurement, which depend on the least count of measuring instrument. A choice of change of different units does not change the number of significant digits or figures in a measurement. This important remark makes most of the following observation clear. For example, the length is 2.308 cm has 4 significant figures, but in a different unit, the same value can be written as 0.02308 meter, 23.08 millimeter, and 23080 micrometer. All these numbers have the same number of significant figure digit 2308. In this case, this 0 is insignificant. In this case, this 0 is insignificant, and this case all the digits are significant. Nothing is insignificant here. Namely 4. This shown that the location of decimal point is no consequence in determining the number of significant figure. Another important point: you don't look at the decimal. Means the decimal will not decide what will be the up to five digit. Then that will not be the criteria for this. We will the examples give the following rules. All the non-zero digits are significant. Means all the non-zero digits are significant digit. All the zeros between two non-zero digits are significant, no matter where the decimal point is, if at all. Because this zero means it is between non-zero digits, so it is significant. You cannot ignore this one. If the number is less than 1, the zero on the right of decimal point but to the left of the first non-digit are not significant. So in example this 0.02308, it is less than 0. Whatever unit we have used, it is less than 1. So on the before 2 and after the decimal, how much 0 will be fall, that will not be the significant. In 0.0230, that is given, the underlined zeros are not significant. The terminal or trailing zeros in a number without decimal point are not significant. The terminal like this 123 meter, if you write in another unit, this will become 1230. But this is not, these zeros are not, does not make any sense. Has 3 significant figures, because and it will also depend on the experiment, whatever the measuring instrument we are using there. However, you can also see the next observation. The trailing zeros in a number with a decimal point are significant. Like in this case, this is a significant, and here also it is significant. Have 4 significant figures each. Decimal point is there, but it is a significant digit. Means decimal will not decide, means decimal point how many significant digits are there. It will be depend on experiment and means the first uncertain digit. 2. We are in the second point. The first point is up to here, these rules. There can be some confusion regarding the trailing zeros. Suppose the length is reported to be 4.700 meter. It is evident that zeros here are meant to convey the precision of measurement, because we are using, suppose we are using the vernier calipers that has this precision, so does not ignore these zeros in that. If the measuring instrument has that much resolution, then we have to write to convey the precision. Therefore significant. If these were not, it would be superfluous to write them explicitly. The reported measurement would be the simple 4.7 meter. Now suppose we change the units, then for Suppose we change the unit here, centimeter this. Since the last number has trailing zeros in a number with no decimal, we would conclude erroneously from observation 1 above that the number has two significant figures while in fact it has four significant figures, and a mere change of unit cannot change the number of significant figure. As I said, the mere change of, if you change the unit means here you will say that it is not significant. Here you will say that these zeros are not significant. Here you will say, but if the measuring instrument has that, using that you are measuring uh, mm, the experiment. If that has that capacity, we cannot ignore that zero. It already it always depend on the measuring instrument that we are using, and the error, the range of errors that are involved with that measuring instrument. To remove such ambiguities, in determining the number of significant figures, the best way is to report every measurement in scientific notation in the power of 10. In this notation, every number is expressed as a into 10 to the power b, where a is a number between a and 10 and the b is any positive or negative exponent or power of 10. In order to get the approximate idea of the number, we may round off the number a to 1. A to 1 for a is less than 5, and to 10 for 5 is greater than 8 and greater than 10. Then the number can be expressed approximately as 10 to the power b. In such, the exponent of power b of 10 is called order of the magnitude of the physical quantity. When only an estimate is required, the quantity is of the order of 10 to the power b. For example, the diameter of the earth is 1.28 into 10 to the power 7 is the order of 10 to the power 7 meter with the order of magnitude 7. The diameter of hydrogen atom is of the order of 10 to the power minus 10. So the order of magnitude is minus 10 here. Thus the diameter of earth is 17 orders the magnitude larger than the hydrogen atom. It is often customary to write the decimal after the first digit. Now the confusion mentioned in A above disappears. 4.70 meter, we will write that 4.700 into 10 to the power 2, and 4.700 into 10 to the power 3 millimeter. 4.700 into 10 to the power minus 3 kilometer. In all these cases, whatever the power of 2, the unit in scientific notation, the 10 to the power is able to absorb all the discrepancy. So in all these cases, we have four significant digits. The power of 10 is irrelevant to the determining the significant figure. However, all zeros appearing in the base number in the scientific notation are significant. Each number in this case has a four significant figure. Thus, in the scientific notation, no confusion arises about the trailing zeros in the base number a. They are always significant. Means the a is the number that will appear in the a, that all are significant. But 10 to the power anything, that we will not count. The scientific notation is ideal for reporting measurement, but if this is not adopted, we use the rules adopted in preceding example. For number greater than 1 without any decimal, the trailing zeros are not significant. If number is greater than 1 and without any, the trailing zeros are not significant here. For numbers with a decimal, the trailing zeros are significant. If number has a decimal, then the trailing zeros are significant. If number is greater than digit 0 conventionally put on the left of a decimal for a number less than 1, like 0.1250 is never significant. However, the zeros at the end of such numbers are significant in a measurement. The multiplying or dividing factor, which are neither rounded nor numbers representing measured values, are exact and have infinite number of significant digits. For example, in r equal to d by 2 and s equal to 2 pi r, the factor 2 is an exact number and it can be written as 2.0, 2.002, 0.000 as required. Similarly, in t by small t by n is an exact number. Means exact number we cannot in exact number we can write as much zero as possible. Now in the next class we will study the rules and some more rules up to 2.7.3, and then in the next class we will cover the this dimension of physical quantities and dimension analysis. That's it for today, this lecture, and we will stop here.